This video is the 6th day of our Extra Topics chapter, and it's the first of 3 days that we're going to be working on capacitors. These 3 days are just a chance for you to get a bit of an introduction to these electronic devices. They're things that you'll study in university, and you'll spend quite a bit of time on them. And so this is just going to be a real quick 3-day introduction to some of the things that they can do and some of the calculations that you'll do using capacitors. First of all, what are they? Don't want to get overly technical here. After all, this is just a little introduction. So I'm going to suggest that their role, they're actually little mini rechargeable batteries. All right, got to pencil that in there. Another way to look at it, and it's kind of a silly little metaphor, but you'll see why I like to say this in a minute or two. Think of them as being parking lots for charge. And if you think about them that way, it'll actually help you just conceptually figure out some of the things that are going to happen with them. In terms of their construction, in the simplest sense, all they are some parallel plates, usually made out of thin little tin foil, sometimes rolled up carefully in like a nice little jelly roll, but they really are nothing more than parallel plates. And we've seen parallel plates before, and how when you charge one positive and one negative, you can create a nice little electric field on the inside. Physically, they come in a few different shapes. They may look something like this. That's one design. They do, though, come in a few different shapes when they're kind of all squished up. The symbol for them, you know that the symbol for a battery is just two parallel lines with one a little bit longer than the other. Well, for a capacitor, we actually draw them as two lines, kind of like a battery, and we don't draw one longer than another. Sometimes, depending on the design of the capacitor, we might curve one of them a little bit, but all you have to do is just draw a couple of parallel lines like that. It really does just represent the parallel plates that you've got. Now, this is just an introduction, these 3 days, but it's probably good if we start cleaning up some of the misconceptions that people have with capacitors right off the start. So I'm going to take these two pieces of tin foil, and instead of having them sit one on top of the other, the way we often have them for parallel plates, what if I kind of spread them out a little bit? And I'm going to run a wire from my battery over to this one, and another wire from that end of my battery over to that one over there. And what we know happens is the negative end of the battery, it's got extra electrons on it, and it's going to try to shove electrons over onto this plate. Now, of course, they don't really want to go, right? Electrons are repelled by each other, and so it's difficult to go and shove them all onto that little parking lot, right? But if you've got some good chemistry push, you can go and do that. Now, what's actually happening is you're extracting electrons from the other plate. It's going to become positive. Now we just draw that instead of worrying about, oh, it's an absence of electrons. We just draw that as if we were adding some positives. And it's completely common and totally acceptable to say that in physics, to say, oh, I've added some positive charge. But of course, we do that by removing the negatives. And then we're putting them over onto that other plate. So I want you to realize that it's difficult to go and smear that negative charge all over that plate because it repels itself. It doesn't really want to go naturally like that. So this is worth a little note in here. I'm going to say that this, and by that I mean this separation of charge, this is difficult to do. Your battery is going to have to really work at it. No play on words intended, but I'm going to take it. You have to do some work. You have to apply a force through some distance in order to push them over there. So that charge separation to make the electrons go this way and the positives, the absence of electrons, go that way is a challenging thing. Now, that's not usually the way we draw capacitors, and it's not usually the way we build them. We usually put the little sheets of tin foil, the little parking lots for the charge, one on top of each other, like that. And then when we charge them up, we're going to go and apply a positive charge here. Of course, again, we do that by removing negatives, but eventually it just gets tiring saying that. So I'm not going to say it anymore. We're going to go and put some positive charge there. We're going to go and put some negative charge there. And a lot of people look at that and they go, oh, well, yeah, the negatives would love to go on that plate to get really close to the positives. And those positives, they'd love to go there to get close to that negative. Yeah, a little bit, but they really don't like being near each other at all. So it's a fallacy to say, oh yeah, the charges like to go out onto the plates like that because then they can get near their opposite charge. That's not true at all. Okay, it's a bit easier to do it that way than it is with the picture at the top of the page there, but it is not generally easy to do. So I'm going to put this in here. I would encourage you to as well. I'm going to say that this, this arrangement with one on top of the other is easier to do, but it's not easy. So yeah, it's easier to do. But don't get me wrong, those charges do not want to go and all pile up with all the positives on one plate and the negatives all on another. But if you put them one near the other, one plate near the other, it's a bit easier than it is if the plates are farther apart. So how about we put in here, it's not, this is easier to do, but it's still not easy. You need a good battery to go and force those charges like that. And then you really do need a good parking lot. You want big, expansive sheets of tinfoil where there's lots of room for that charge to go. And the actual quality of this device that's going to store the charge is something called the capacitance. We're going to represent that by the letter C. So C stands for capacitance. And it's really just a measure of how easily it stores charge. So it's difficult to store charge, but some of these parking lots are nice and big and wide, so it's easier to store the charge. The units for capacitance, named after an old physicist, the units are farads. And the abbreviation for that is a capital F because it's named after somebody. And there's a quick little calculation you can do in order to figure out how much capacitance you'd have with a couple of sheets of tinfoil that are fairly close together. The calculation is capacitance is equal to, there's a K that's going to depend on the stuff that's between the sheets. And then there's a constant of nature, epsilon naught, the permittivity of free space. And then here comes the interesting stuff that you can easily adjust. A is going to be the area of the plates, and D is going to be the gap in between the plates. So just looking at that fraction, what I can see is more area. Again, think parking lots. More area is going to give you more C. It's going to give you better capacitance. So for a given battery, you can store more charge. Now the D is down in the bottom. So if you have less of a gap, if you have a smaller gap, right, a smaller value for D, that would also give you more capacitance. What happens there is, it's again not easy to get all those positive charges together, but if you get those plates really, really close, then there is a little bit of an effect where, yeah, the positives don't mind going there because they're close to some negatives. They still don't like it, and you still have to push, but it's a bit easier. So D is this gap in there, and then A is the area of that plate. It's the area of the kind of the overlap of those plates. Now K depends on the material that's in between the plates, and for us, for AP Physics, we're just going to have air in there. So I'm just going to let you know that K is equal to 1 for air. But you can get some exotic materials that you can put in there that have really nice high K values. And that allows you to have a bigger capacitance, so you can store more charge with the same battery. Okay, speaking of storing charge, let's take a look at what happens when you do charge up a capacitor. You're going to want to grab a battery because you're going to have to push that charge on there. Now you should probably put a resistor in here simply for safety so it doesn't charge too fast. And then we'll put the other wire over to here. So yeah, again, this resistor here, I'm just putting that in there for safety. Okay, we're going to end up with some Q here because we're going to steal some electrons away. And I'm going to call that the positive Q that we've put onto that top plate. Now you end up putting a corresponding amount of negative charge onto this plate down here. So you have this negative Q there. It's the exact same amount of charge that we put on both of those plates. We just end up with a positive charge on one and a negative charge on the other. Now here is a nice little formula that lets you know how successfully you can put charge onto that capacitor. And we're just going to use the letter Q in this formula for how much charge in general, whether it's plus Q on the positive or negative Q on the negative, whatever. The equation is this: the amount of Q, so that's either that red Q or the black Q, it's the same amount, is equal to the capacitance multiplied by the voltage. So what I can see is, if you want to store more charge, that way you can use it later, get a bigger parking lot, get a better capacitor, right? So a bigger C is going to give you more Q that's available to be stored up. The other thing that I can see is it does depend on the voltage of the battery, right? So you go to the store, you buy yourself a battery, and that battery is what's required to push that charge onto that plate, because it does not want to go, even when the plates are close to each other. They still don't really want to have all those charges go to one side, to one plate. But if you've got a good battery, you can push them there. So I would say this: more voltage, a bigger battery, forces more charge. On the capacitor. Hey, here's a little abbreviation for you. We often just call them caps. So a bigger voltage, a better battery is going to force more Q onto that capacitor. Now, that equation's beautifully linear. So what I can see is, if you're tracking, hey, how successfully can I put Q, and by Q I mean, either that number or that number. Same thing, it's the same number. How successfully can we go and put some Q onto that set of plates for a given voltage there? And what I find is this is just a nice, beautiful straight line. So the picture ends up just doing something just kind of like that. So the more voltage you have, the more Q you can actually get there. Now, when it charges up, one of the things that happens is at the very beginning, there are no charges on those parking lots yet, and the battery is pretty quick and efficient about moving some of the first Qs onto the parking lot. But then, as the Qs start to build up, positive on the positive plate, negative on the negative plate, you start to get this repulsion where the battery's forcing them, and it's like, whoa, they don't really want to go, because the capacitor's starting to build up a voltage that's like the battery, but now it's fighting us. It's stopping us from pushing those charges onto the plates. And so the Q at the beginning goes on very quickly. So the Q divided by T, the current is actually quite high at the beginning, and then it kind of levels off like this. So it's this weird kind of exponential decay, but upside down, as we go and actually charge up this capacitor. And so there's this peak value that we're going to be aiming for. And it takes, well, mathematically, it takes forever to get there. It's one of those upside down exponential decays. So this red line, that red line is the Q is equal to CV kind of value, right? For a given voltage, it'll get there, but it'll basically take forever. Pictorially, if we wanted to kind of draw that, it would look like this. You've got this capacitor, right? It's a couple of parking lots, right, for the charge, right? So the wire's connected. At the beginning, there's no charge there at all. And if you were to take a voltmeter and go and connect up that voltmeter to those capacitor plates, pretty common thing to do, right? So you run some wires like that. This voltmeter at the beginning would say, oh, well, there's no Q on that capacitor yet, so there's no voltage. Then that battery starts pushing some Q onto the plates. Okay, so it's starting to happen. We're starting to see a few positive Qs show up on that plate and a few corresponding negative Qs down on that plate there. And this battery is now starting to give this capacitor some voltage. So if you were to check out a voltmeter on that capacitor, it might say, oh, I'm up to 10 volts. But maybe it's like a 24 volt battery. And so you keep pushing. But now you've got this 10 volts that's kind of fighting you with your 24 volt battery. So the next little bit of Q dribbles on a little bit slower. And then slower. And then slower. So it'll take basically forever for you to get up to whatever the voltage of the battery is. Maybe it's a 24 volt battery. So a few last little thoughts on this page. That capacitor now starts to develop a voltage, and it's really just abiding by that Q equals CV. But as the Q comes up, so does the V. So more charge on the cap gives the cap more voltage. So it is like a little rechargeable battery, but with a very dynamic voltage that grows and grows and grows as the Q builds up. Now, another way to look at it, if I only have a 1.5 volt battery and I would like to store a lot of charge, I want a lot of coulombs available, then 1.5 volts isn't very big. But maybe you can get some big sheets of tinfoil, so that 1.5 volt battery could actually put a pretty decent Q out there. You know, the equation is Q is equal to CV. So if you don't have a good V, just go with a really good C. Go with a really good capacitor. So I'm going to say this, a bigger capacitor, a bigger cap, will store more Q for a given voltage, for a given battery. So if you only have one battery and you want to store up a lot of Q, get a nice big capacitor. That would actually be super helpful. Okay, next little issue. We're going to talk about something called time constants. Okay, it's going to be something that you'll talk about at university for sure. So let's talk about it here too. If I do have, let's make some numbers up. Let's say I've got a 6 volt battery, and I'm going to go and connect it up for safety with a resistor in there, maybe a 2 ohm resistor, and another little wire over there. Okay, and so we're going to watch what happens. Here's the same story, just being operated over and over again. Two ohms for safety. Gotta put something in there so it doesn't charge up too fast. At the very beginning, the voltage on this capacitor is 0 volts. It has no Q on it yet. Not yet. We've just connected the wires, just now. So there's no Q that's been forced onto them yet. And if I was to go and check out how fast the current's going to flow right after I connect that wire, what I'd find, just using Ohm's law, I've got V divided by R, got a 6 volt push, 2 ohms of resistance, I've got 3 amps, 3 coulombs per second. It's going to start moving down the wire. We're going to take negatives from one plate, push them over to the other, and so what happens is we start to end up with this plate going a little bit positive and the plate down here going a little bit negative. Now, I probably haven't put a lot of charge on it yet, but maybe while I'm using this 6 volt battery, maybe at that amount of charge level, the capacitor is built up to 3 volts. It's working its way up to 6. So at this point, if I check out Ohm's law, well, I've got 6 volts pushing, but 3 volts pushing back. So I've actually only got 6 minus 3. I've only got 3 volts effective. So 3 divided by 2, I'm down to 1.5 amps. So it'll keep charging, but now it's going to charge slower. It's kind of like a hot object, you know, sitting outside cooling off. Cools off aggressively at the beginning because there's a big temperature difference, and then it cools off at a slower rate because there's less of a difference. Well, we're going to see that happen here too. You know, eventually, if you wait forever, like literally forever, this capacitor will reach 6 volts. And at that point, it will no longer keep charging up because you would have your 6 volt battery, and then you'd have a 6 volt capacitor that's fighting back. So you'd have effectively 0 volts, 2 ohms, you'd have 0 amps. So it charges aggressively at the beginning and then slowly later. So you end up putting a lot of Q on at the beginning and then slowly later. So if you were to be monitoring that voltage on the capacitor, which is actually just the amount of Q multiplied by the C that we've got there. Oops, sorry, hang on. I don't think that's quite right. Let's try that again. Let's just say this. Let's just call this the voltage. I had that backwards. Let's say we've got the voltage here on that capacitor, and then we'll monitor time this way. Then what you're going to find is that 6 volts is kind of a goal that we can shoot for right here. So I'm just going to grab a ruler here, draw on a little destination, a little goal line. Right, we're aiming for here, but it's going to take some Q in order to get there. The V would actually be the Q divided by the C. But when we do the calculus of this, for this differential equation, what we find is that it does this. And then it just gets closer and closer asymptotically to that line. It's exponential decay, but just upside down. So the calculus of it, for that exponential decay, and you'll see this at university, the calculus of it ends up having an exponential in there that decays away. So it's going to have a negative to it. And you're going to see that it ends up having time. So the more time you wait, the more that exponential evolves. But then it's divided by this thing called the time constant, kind of like a half-life. Close enough to being a half-life that it's probably worth saying that. Okay, so this is like a half-life for radioactivity. And so we call that tau, that Greek letter, we call that the time constant. And it depends on a couple of things. So this is something that tells you how long it takes to get to a factor of 1 over e, sort of closer to your destination. And it slows things down if you have a bigger resistor. Bigger resistors will cause less current to flow. So the time constant is definitely affected by the resistance, but it's also affected by the size of the parking lot. A big parking lot is going to take longer to fill. So in this story here, the time constant is actually the resistance that you've got for safety multiplied by the capacitance that you've got for those pairs of parking lots there for putting the charge on. So a bigger R or a bigger C or both is going to actually cause a longer time constant. It's going to push the story farther down the road. So you might have a graph like I've got there in blue for one capacitor charging up, or maybe you might end up with a capacitor that has a shorter time constant and it might charge like this. So this is a small time constant. And in blue, you'd have the exponential decay, kind of an upside down decay. This is a bigger time constant. It's taking longer to have that factor that we are away from the red dotted line changed by 1 over e. So let's put a couple of notes in here for that. Okay, so we've got this 6-volt battery. And got a resistor in there. We said 2 ohms. Okay, great. And so it's going to take some time in order for it to charge up. So what could we do to change things? Maybe in this story, the capacitance here, maybe the capacitance is equal to, 5 farads, which by the way is huge. Capacitors are usually much, much smaller than that. So we could make a change to this story. We could go with a bigger resistance. What if we said, let's change this to 20 ohms. That's going to take longer to charge this up if it's the same capacitor of, say, 5 farads. There's another change we could make. Right? We could have left it at 2 ohms. But what if we change this capacitance? Maybe we make the sheets bigger, or maybe we put the capacitors, the sheets closer together. Maybe we make this capacitance 12 farads, something bigger, like bigger parking lot. Okay, either of those two changes will increase the time constant. Okay, so probably worth a little note in here. Increasing R or C will increase tau. The time it takes to get a little closer to being fully charged. Now, the way the calculus works with those differential equations with that upside down exponential decay is this. Technically, it takes forever to charge. Okay, so I'm going to put that in here. It takes forever to fully charge. Well, we can't wait forever. So we have to ask ourselves, when is it mostly charged? So a pretty common practice in electronics is to say it is, I'm just going to put in kind of air quotes here, charged, like, hey, we're kind of finished with it. It's pretty close to being fully charged up, close enough to drive away. It's charged after 5 time constants. So you can actually calculate that value for tau. It comes out in seconds. And if it says, oh yeah, the time constant is 4 seconds, then if you were to wait 4 times 5, if you were to wait 20 seconds, sure, the capacitor's not totally charged, but it's so close, you might as well say it's charged. So 5 time constants is a pretty conservative amount to wait in order to say, yeah, it's pretty charged up. Well, last thing for this video, once you have that pair of parking lots here full of charge, positives here, basically up to the voltage of your battery, maybe it's 6 volts. Once you've got that ready to go, you can take that charged up capacitor and you can now go and connect it up to a device like a light bulb, and it will work. That light bulb will light up. Maybe not for very long, but it will actually light up. And what's happening now is the charge is actually going to go back to 0 on those plates. The electrons will leave the negative plate, head back and neutralize the positive plate, and eventually it will head down to zero charge and 0 volts. Now we're going to do some graphs here in a second of, hey, what happens with the Q and the voltage, and what happens with the Q left on the capacitor and time as we wait. So let's just kind of draw this out here a little bit. I've got my light bulb or some sort of resistor in here for safety, and I'm going to connect up those plates like this. Here it is again. Connect it up to that resistor. Maybe it's a light bulb. And at the beginning, got this thing fully charged. Lots of charge separation going on here. And then what happens is that when you connect up that light bulb, wow, you get a lot of current flowing, right? So the I goes this way. Of course, don't tell anybody. It's our one big mistake in physics, but really the electrons are just going the other way. Well, as those electrons start to leave, then the overall amount of Q on those plates starts to drop. A little while later, it might look like this. But remember, with Q comes voltage, because with voltage came Q. It took a big voltage to push the Q onto the plates, and now as the Q comes off, the voltage of that capacitor starts to diminish. So the current leaving now is going to be a little bit less, because there's less Q, so there's less voltage. And then later on, maybe there's just barely any Q left. So if you were to put a voltmeter on this capacitor, which is what you've got down below there, it would be barely recording any voltage at all, and there would be barely any current, going through that device, through that light bulb. And so you'll see this voltage go from, a fully charged capacitor voltage, and then it starts dropping down, and then it starts dropping down, and it's going to diminish as the Q diminishes. So because of that relationship that says Q is equal to CV, with a good V comes a good Q to push onto the plates, and with good Q on the plates comes a good voltage to be registered by a voltmeter. You get this nice linear line, the slope of which is related to the capacitance. And if you're fully charged, maybe you're way up here, right, with your kind of good peak voltage, right, and your peak Q, when you charge that capacitor up, what happens now as you discharge it is you end up walking your way down the graph like that. And there's less and less Q left, so there's less and less voltage. So there's less and less current, so the actual discharge rate diminishes, and you end up with not even an upside down exponential decay, just a true exponential decay now that looks like this. And it's going to have that same exponential, right? That e to the negative t divided by tau, that time constant is going to show up there again. And so it technically takes forever to fully discharge the capacitor. And again, we're not going to wait forever. We're going to wait 5 time constants. So I will say this, though, as we finish up here for this one today, it takes forever to fully discharge. But you know, after a little while, you can pretty much say there's nothing left. So we usually say in electronics, it is essentially discharged after 5 time constants. So you can calculate what the time constant is. It's just the R times the C. It's a number that's in seconds, and multiply that by 5, and you can basically say you're done at that point right there. And that's where we're going to stop at this point. We'll pick up and do 2 more days of working with capacitors.